You want to know the truth about Mars and the Moon. Let's start with one question. How is Mars different from the Moon? You've heard this line 1,000 times. We went to the Moon. Mars is just a little farther away. It sounds reasonable, but it's completely wrong. And if you're willing to look just one layer deeper, your entire intuition will collapse like dry sand underfoot. You see, the Moon is a straightforward problem. Zero atmosphere, weak gravity, a distance so close that if something goes wrong, you can still manage. It's a technical challenge, difficult, but clean and tidy. Mars is something else entirely. It has an atmosphere, but it's too thin to help and too thick to ignore. Higher gravity, a journey lasting nearly a year, and a distance so great that turning back only exists in history books. Right from the first line, Mars doesn't ask if you have enough technology. It asks if you understand the math. And if the answer is no, you'll never come back. If you really want to understand why returning from Mars is nearly impossible with current technology, you have to confront a figure that every engineer from NASA's 1960s era to today's SpaceX both respects and dreads: the Tsiolkovsky rocket equation, written in 1903, but still ruling the entire space industry like a stern king. And you know what's funny? More than a century has passed. Humans built the Saturn V, Space Shuttle, Falcon 9, yet no one has escaped that single-line equation. A rocket, whether it's the 110-meter-tall Saturn V or a little model you launch in your backyard, does exactly one thing: throws mass backward. Newton said it back in 1687 in the Principia, and he was never wrong. Action equals reaction. You want to go up, you have to throw something down. But here's where everything starts getting brutal. You have to carry the mass you're planning to throw. Carrying it makes you heavier, so you need more mass to reach the same speed. And then you need even more mass to throw the extra mass you just added. The Saturn V, the most powerful machine humans have ever successfully launched, weighed 2.9 million kilograms at liftoff. But the part that actually reached the Moon was only about 4,500 kg, less than 0.2% of the total mass. That's the mass ratio laughing in your face. And what makes everything even harder is the logarithm in the equation. Delta V equals sine V got ln mn day cell, adding 1, 2 kilometers per s of speed isn't a little more fuel. It can demand 3 or 5 times the existing mass. The Apollo ships needed about 15-16 kilometers per s delta V for the entire mission, so the Saturn V was just barely enough to survive. But to return from Mars, we're talking 18-22 kilometers per s, and the logarithm, unlike humans, doesn't soften for dreams of exploration or heroic spirit. It only cares whether you have enough mass. And if you don't beat this equation, you'll never leave the surface of Mars, no matter how much courage you bring. When people talk about going to Mars, they love bringing up the Apollo story, as if it's the ultimate proof that we did it once, so of course we can do it again on a bigger scale. But if you look at Apollo through the eyes of mathematics, you'll see something completely different. Apollo succeeded because the Moon is a cute, kind, polite problem. A problem where nature gave us a tiny crack to slip through, as long as we were extremely clever. Start with the Saturn V, that 110-meter-tall monster, weighing nearly 3,000 tons, about 85% of which was fuel. That number isn't waste. It's the minimum fuel needed to generate 15-16 kilometers per s delta V, the speed required to leave Earth, enter orbit, then perform the TLI burn to send humans out of Earth's sphere of influence toward the Moon. Everything was measured and weighed down to the kilogram. But the reason the Saturn V could do it wasn't because it was overwhelmingly powerful. It was because the Moon didn't demand more. The Moon has no atmosphere, and that seemingly small detail is a huge gift. You don't have to fight drag Don't need complex deceleration systems. Don't face the heat from plunging into a paper-thin atmosphere that's still enough to melt everything. Like Mars, you just fire the engines, control velocity, and land. Hard, yes, but it's engineering hard, not rocket equation hard. Then there's gravity. The moon has only 1/6 Earth's gravity, meaning you don't need a giant ship to leave it. What brought Armstrong and Aldrin back to orbit was a tiny module weighing about 2.3 tons, light enough that you look at it and wonder how this thing could lift 2 humans off a celestial body. But with gravity that weak, it was enough. Nature gave the green light, and staging, artfully discarding mass, was Apollo's secret weapon. The Saturn V had 3 big stages. Each one burned out and was dropped like sandbags you shed to climb higher up a mountain. Every discard reduced mass, and reducing mass is the only thing that lets you beat the exponential part of the rocket equation. The moon mission was almost designed around this idea. Use mass when needed. Discard it the moment you're done. Never carry useless empty sections into the next phase. And during landing, you kept applying that logic. The descent module stayed on the moon. The ascent module flew up to meet the command module. Another form of staging. The moon allowed staging to work smoothly, beautifully, perfectly, like a math problem solved in a few elegant steps. And time. This is the enormous difference. Few people bother to think about. The trip to the moon took only about 3 days. 3 days means you don't need to carry tons of food. Don't have to worry about cosmic radiation pounding you for 8 months. Don't treat every tiny mistake as a death sentence. And the best part, you can turn back. Apollo 13 proved this powerfully. An accident happened, and thanks to the free return trajectory, they could use the lunar module as a lifeboat, loop around the moon, and come home. If that same accident had happened on a trip to Mars, where every second you fly dozens more kilometers away from Earth, there would be no turning back, no one to rescue you, and no miracle like Apollo 13. All of this zero atmosphere, weak gravity, favorable staging, short travel time, rescue possible distance, created a problem humans could solve. Not easy, not simple, not a miracle from primitive technology, but a problem where every mathematical factor stood on our side. And that's the key point so many miss when talking about Mars. Apollo didn't prove the universe is easily conquered. Apollo proved that when you pick the right problem, a problem where the numbers don't torture you with an evil logarithm, a problem where nature temporarily relaxes the rules, humanity can achieve beautiful things. The moon was that kind of problem. Mars is not. Mars starts with a cold calculation, whose result is almost always no. And now we need to talk about one of the most important concepts in all of space travel, the thing most people think they understand, until they actually look at the numbers, delta V. It sounds like just change in velocity, too simple to cause trouble. But delta V is where human intuition, nurtured by life under 1G, and atmospheric friction, begins to collapse without mercy. Imagine you're in a small boat on a lake. You want to go from point A to point B, and you know that if you row twice as hard, you'll get there twice as fast. On Earth, in everyday life, most relationships are nearly linear. Double the effort, the result roughly doubles. But in space, especially when changing orbits, nothing is linear anymore. Delta V operates under alien rules, and the rocket equation is always standing there, waiting for your tiniest mistake to amplify it dozens of times over. A simple example: to reach low Earth orbit, you need about 9.5 kilometers per s delta V. Doesn't sound too bad, especially since the Saturn V achieved 16 kilometers per s. So if you want to add a few more kilometers, say up to 12 or 13 kilometers, what's the big deal? And here's where your intuition, built from riding bikes, driving cars. Running starts betraying you, because delta V isn't a little more speed. It's energy, and worse, it's energy for a system that has to carry its own fuel. The result, in space, adding a few kilometers isn't like pressing the gas a few percent harder. It shatters your mass ratio. With the exhaust velocity of today's chemical engines, around 4.5 kilometers, increasing delta V from 9 kilometers per s to 12 kilometers per s doesn't mean adding a bit more fuel. It means doubling or tripling your initial launch mass. And if you want 14 or 15 kilometers per s, the required mass could jump 4 or 5 times. That's not pessimistic guessing. That's how the logarithm works. When you look at Tsiolkovsky's equation, delta V equals sine V deltas ln m0/m1, you immediately see the cruelty hidden inside. You can improve engine efficiency a little, but ln m0/m1 is the one deciding life or death. If you need 20% more delta V, sometimes you have to increase mass by 200%. And if you need 40% more, the mass increase might become impossible to build in reality. This is why a ship can go to the moon, but not to Mars, using the same structure. A moon mission requires total delta V of about 16 kilometers per s. A Mars round trip can demand 22 kilometers per s. A difference of just a few kilometers, but the consequence is like saying, I only gained 5 kilograms, and then discovering you have to buy a whole new wardrobe, replace your bed size, and widen your house doors. Delta V doesn't play with you in small proportions. It amplifies everything. Try picturing a more everyday example. You're carrying a 10 kilograms backpack to climb a mountain. If someone says climb 10% higher, you think, sure, just a bit more. But delta V doesn't work that way. In its world, climbing 10% higher might require you to start with a 30 kilograms backpack. The problem isn't the climb. It's that you have to carry the thing that lets you climb. And the thing that lets you climb needs more things to carry it. This is a chain of positive feedback. Fuel to carry fuel. And it doesn't stop until you can't meet the initial mass anymore. That's when your design becomes impossible. That's when engineers start talking about tens of stages, fuel depots, in situ resource utilization, all things that sound modern, but are really desperate attempts to cheat the equation. And here's what you must remember. Your intuition was trained on Earth, where speeds rarely exceed a few hundred kilometers, where friction keeps everything stable, where you never have to carry your own oxygen to breathe, or fuel to survive. In space where everything is vacuum, where there's no natural drag, no surface to push against, delta V becomes the supreme language, and your intuition is completely useless. Adding 3 kilometers per s isn't a little. It's the difference between a feasible ship and one as heavy as a skyscraper. And when it comes to Mars, delta V is that fragile boundary, just a few kilometers, but the gap between we can do it and completely impossible is far larger than you think. Delta V doesn't care how excited you are. It only cares if you have enough mass to pay the price. And to see clearly how delta V decides the fate of every space dream, we have to look closely at the Saturn V, the machine that took humans to the moon, and at the same time showed us a truth many don't want to face. This wasn't the key to unlocking the universe. It was just a narrow bridge leading to one single point, the moon, and not much farther. The Saturn V looked like the symbol of absolute power, but in reality, it was a work of art in barely clearing mathematical limits, and its entire secret lay in 3 words: multi-stage rocket. That structure wasn't for looking impressive. It was the only way to defeat the exponential part of the rocket equation. Let's peel the Saturn V like an onion. Stage 1, SIC, over 2,300,000 kilograms, with 5 F1 engines burning 13 tons of fuel per second. Its sole job was to drag that enormous steel and fuel beast through the first 2 minutes, the phase when Earth pulls hardest. When the fuel ran out, it was dropped, fell into the ocean, and never returned. No one kept it for savings. It was the first sacrifice to reduce mass. Stage 2 stars, lighter, but still holding nearly 450,000 kilograms of fuel, continued pushing upward, reducing gravity's grip, and preparing for orbit. Burned out, it too was discarded. Then stage 3, SIVB, about 110,000 kilograms of fuel. It placed the ship in orbit and then performed the critical burn, translunar injection, pushing the ship away from Earth at about 10.8 kilometers per s. When this stage burned out, it was also left behind, like its older siblings. By now you can see clearly, the Saturn V didn't win with brute strength. It won by shedding mass at exactly the right moments. It was an elegant dance of dropping empty stages below, lightening the load so delta V could reach what was needed. If you tried to go to the moon with a single stage rocket, no staging, you'd never leave Earth. Not because the engines were weak, but because the rocket equation declared, no, math doesn't let you win with brute force. And this is what people forget when thinking about Mars. They say, just make a rocket bigger than the Saturn V, and we're good. But that's a cute way of saying, we'll just build a house 3 times bigger, and surely reach Mars. They don't understand that the Saturn V could only take humans to the moon because the entire problem fit perfectly within its feasibility window. You needed about 16 kilometers per s delta V. You only carried a small amount of hardware that actually had to go to the moon. Destination gravity low. Destination atmosphere 0. No need to carry return fuel. No need to live on the moon for 500 days. No requirement to land 40 tons of equipment. In other words, the moon mission was a problem custom written for the Saturn V, and the Saturn V was the clever solution, just sufficient to clear every exponential threshold. But the moment you change the destination to Mars, all of the Saturn V's logic evaporates. You need more delta V. And as I just explained, delta V doesn't increase linearly. Adding 3-4 kilometers per s isn't as simple as adding one more fuel tank. It could require tripling or quadrupling mass. You need to carry landing hardware, weighing tens of tons, not a few tons like the LEM. You have to fight a thin, but still heating atmosphere. You have to live there over 500 days, waiting for the launch window. And you have to take off again to return. A requirement never faced by any mission except Apollo. But Apollo took off from 1/6 Earth's gravity, not 38% like Mars. And imagine this scene. To deliver 1 ton to the Mars surface, you might need over 20 tons in low Earth orbit. If you want to deliver 30 tons to Mars, to prepare for a return trip, you might need 600 tons in LEO. If you want to carry return fuel, the number gets even bigger. Can you see the problem yet? The Saturn V had a total mass of about 3,000 tons. A traditional Mars mission configuration could require 20,000, 40,000 tons. No factory on Earth has ever produced anything close to that number, and no launch pad could handle it. This is why I call the Saturn V a narrow bridge to the moon. It was beautiful, powerful, an unmatched human engineering achievement, but it is not the road to the wider universe. It was just one bridge across one single chasm to exactly one place that mathematics permitted. And when you stand on this side, looking toward Mars, you'll realize it's not just about a bigger bridge. It requires a different law of physics, one we don't have. The Saturn V doesn't give us hope that just make it bigger and we win. The Saturn V teaches the opposite lesson. When you happen to pick the right problem, a problem the rocket equation doesn't hate, You can create miracles. But Mars is not one of those kind problems. If the Saturn V was the narrow bridge that got us to the moon, then the first thing you realize when looking toward Mars is that bridge, no matter how far you try to stretch it, cannot cross the distance. Not the just a little farther kind of distance, but the kind of distance that causes the entire human survival strategy to collapse. Let's start with the easiest comparison. The moon is about 384,000 kilometers away, and Apollo took 3 days to get there. 3 days are longer than normal weekend, and you're on another celestial body. If anything went wrong, you still had a chance to turn back, or at least limp home, using a free return trajectory. Apollo 13 proved this in a tragic yet beautiful way. When the oxygen tank exploded more than 300,000 kilometers from Earth, they could still return thanks to the lunar loop trajectory and gravitational assist. 3 days is a time frame in which a mistake hasn't yet sentenced you to death. But Mars is at a minimum 55 million kilometers away, and that's when the two planets are in their ideal positions. Usually the distance ranges from 100 to 300 million kilometers. With current chemical propulsion technology, the journey to Mars takes 8 to 9 months, and that's assuming everything goes perfectly, according to calculation. 9 months floating in vacuum is unlike any experience on Earth. This isn't a long flight. It isn't an intercontinental journey. It's locking 4 to 6 human beings inside a sealed metal box, a few dozen meters long, traveling through an endless black ocean, where every millisecond carries you dozens more kilometers away from Earth. And this is where the difference becomes cruel. There is no abort, no rescue, no turning back. Once you perform the burn to leave Earth orbit and head toward Mars, you're like a bullet that has left the barrel. The universe does not allow mid-course U-turns. To turn back, you would need delta V equivalent to continuing all the way to Mars. In other words, impossible. Not just impossible in terms of fuel, but impossible in terms of orbital mechanics. You're on a gravity-determined curve, and to escape it, you have to pay a price no ship can afford. At distances of tens of millions of kilometers, if an Apollo 13 style emergency occurs, NASA cannot send a rescue craft. Not because they don't want to. The universe simply doesn't allow it. A rescue ship would take many months to arrive, while the crew might have only hours or days before life support collapses. There is no one nearby to help, because near in space is an utterly merciless concept. 10,000 kilometers away is the same as 10 million kilometers away. If neither can change course, and perhaps what humans underestimate most is the psychology of being stripped of the option to turn back. When you know you cannot return, cannot stop, cannot open the door and step out, cannot receive help in any situation, that feeling is not ordinary loneliness. It is a foundational truth that the human brain was never designed to confront. On Earth, you always have a psychological anchor. Car breaks down. You pull over. Plane has trouble. Pilot finds a place to land. Fire starts. You run outside. All your biological systems are built around the idea that there is always some way out. But in deep space, on the way to Mars, the notion of an escape route does not exist. You don't open the door unless you want to die instantly. You don't call for rescue. You don't change course. You don't have a safer tomorrow. You have only yourself, a metal ship, and 8 to 9 months drifting in a black ocean, where if you scream, not a single atom carries your voice anywhere. And when I talk about psychological impact, I'm not talking mild stress. I'm talking about 4 or 6 people hearing each other's breathing 24 hours a day, facing silences so long you can hear your own heart pounding in your nose, facing the fact that any mistake, no matter how laughably small, could kill everyone. NASA has conducted many isolation studies in simulated environments, ICES, Mars 500, and similar experiments. The results are always the same. The human psyche is not suited for long-term space. We can cope for weeks, maybe months in confined settings, but 9 months continuous, then 500 days on an alien planet, then another 9 months back. That is a lifetime's worth of pressure compressed into one mission. And when all of this combines, distance, time, the human brain, and inflexible laws of physics, you realize that the hardest part of Mars is not landing, not surviving on the surface, but the true meaning of leaving Earth for a place where turning back is no longer an option. Mars is not just far in kilometers. It is far from the entire survival intuition we have carried since we lived in caves. Mars erases the foundational sense of safety that every creature on Earth relies on. And that is why distance is not just a number. It is a psychological and technical death sentence from the moment you press the launch button. And once you understand that the journey to Mars offers no turning back, you see that everything hinges on a single number, delta V, to get there. And delta V is never kind to those who are careless. First, to go from the surface to low Earth orbit, you pay the familiar price, about 9.5 kilometers per S delta V. But to leave LEO and perform trans-Mars injection, the big burn that puts you on the transfer orbit to Mars, you need another roughly 3.6 kilometers per S. This is the single most critical burn of the entire trip. Miss it by even a little, and you miss Mars entirely, and drift into a lonely solar orbit as a piece of metal that never comes back. Upon arrival, you need Mars orbit insertion, costing another 2 kilometers per S delta V, to slow down and let Mars capture you into orbit. That means, for the outbound leg alone, you need an extra 5-6 kilometers per S delta V, compared to just reaching LEO. Sounds simple. One more burn, a few more condensants, no big deal. But as you saw earlier, delta V is never no big deal. Delta V is the expert at turning tiny mistakes into tragedies. At interplanetary scale, every error, even the kind you think is not worth noticing, grows exponentially in 2 ways: directional error and velocity error. Imagine me standing in a Caltech classroom, chalk in hand. If I throw the chalk 1 degree off target in a 10-meter room, nobody notices. But if I throw it and it travels 55 million kilometers, like a Mars journey, a mere 1 degree error puts it millions of kilometers off target, enough that you never see Mars in your sights. And unlike the chalk, your ship cannot steer back reasonably. Why? Because course correction requires delta V. To fix a 1-2 degree heading error, you burn hundreds of MDAS of delta V. To fix a 5 degree error, you may need a full 1 kilometer per S, and you cannot carry extra fuel, just in case, because as we've seen, extra fuel requires more fuel to carry the extra fuel, and your launch mass explodes exponentially. The heavier the ship, the more vicious the mass ratio, and mass ratio never negotiates. Delta V doesn't just make you miss Mars, it makes Mars kill you. Think about MOI, Mars orbit insertion. If you don't decelerate at the right moment with an error margin of only a few MDAS, you will either fly right past Mars and be lost forever in space, or plunge into the atmosphere too fast and be incinerated by friction heat, because Mars's atmosphere is neither thick enough to slow you gently nor thin enough to ignore. A burn 1-2% too strong can drop you too deep, 1-2% too weak, and you aren't captured by gravity. I once joked to students, going to Mars is like jumping onto a bus moving 60 miles an hour, and you get only 1 jump. Miss by half a footstep, and you don't grab the handrail. You hit the pavement, and someone calls traffic police. And that was me making it sound easy. In reality, Mars isn't a bus. It's a sphere flying 24 kilometers per s around the sun, while you're also orbiting the same gravity source. You and it meet only in an extremely narrow window, and delta V is the ticket that lets you step through that window. One of the things that amazes people about NASA isn't landing or launching. It's the ability to predict that a spacecraft launched in 2005 will rendezvous with Mars at exactly the right spot in 2006, be off by just 0.01%, comma, and Mars appears somewhere else. The universe has zero patience for small deviations. Now picture this. To reach Mars, you need an extra 5-6 kilometers per s delta V. It sounds tiny, next to 300,000 kilometers to the Moon, or 55 million kilometers to Mars. But delta V doesn't care about distance. It only cares about your mass. And that mere 5-6 kilometers per s extra can force your mass to increase 3-4 times compared to Saturn V. That turns the idea of just build a bigger rocket into physics comedy. A 10,000-ton rocket doesn't get you to Mars any better than a 3,000-ton one, because delta V isn't measured in power. Delta V is measured in mass ratio, and mass ratio is exactly what explodes exponentially when you need just a tiny bit more velocity. And if delta V is already making you feel a little short of breath, congratulations, you're about to meet the next opponent of every dream of setting foot on Mars. Its atmosphere, one of the strangest collections of molecules humans have ever had to deal with. It's not thick like Earth's, so you can parachute down safely, but it's not thin enough to ignore completely like the Moon's. No, Mars's atmosphere sits exactly in the dead zone that makes every NASA engineer want to request a transfer just hearing about it. First, density. Mars's atmosphere is about 1%. The density of Earth's at sea level. That means if you open a window on Mars, you still die from lack of oxygen. But if you throw a paper airplane, it doesn't go anywhere because lift is almost zero. 1% density means parachutes are nearly useless for heavy objects. A giant 15-meter diameter chute might be enough to slow a 900 kilograms robot like Curiosity. But if you try that on a 20-40-ton crewed spacecraft, your parachute would have to be the size of a football field. And even then, it wouldn't generate enough drag to reduce velocity from 5 kilometers per s to safe levels. But here's the paradox. While the atmosphere is too thin to help you slow down, it's still thick enough to burn everything up. Nowhere else in the solar system forces you to equip a heat shield to deal with an atmosphere so weak it can't even perform the basic job of an atmosphere. Mars makes you carry a heat shield weighing hundreds of kilograms because friction heat during atmospheric entry can still reach thousands of degrees C. That means you have to carry a useless parachute and a mandatory heat shield because without it you die. And when both have done their job and you're still coming in too fast, you are forced to use retropropulsion, firing engines backward to slow down. And this, ladies and gentlemen, is when the rocket equation pats you on the shoulder again. How much do you want to decelerate? How much do you want to burn? Burn that much, you have to carry that much. Carry that much, your ship gets that heavy. Ship that heavy, you need even more fuel to carry the fuel. This is the level of absurdity that even makes me laugh. Mars's atmosphere doesn't help you slow down, but it forces you to carry extra equipment that makes you heavier, making deceleration even harder. It's math of the more you try to fix it, the worse it gets. Variety. And once you've added mass for the heat shield, added mass for the parachute, added mass for retropropulsion, then mass pulls in fuel, fuel pulls in mass, mass pulls in fuel. The familiar loop you've seen too clearly. And if you want to know how serious it is, listen to the number NASA gives. To place 1 ton of payload on the Mars surface, You need about 20 tons in low Earth orbit, 1 ton on Mars, 20 tons in LEO. That number makes engineers lose hair, not from stress, but from constantly scratching their heads to see if there's any way to cheat physics. And trust me, physics isn't easily cheated. No current technology can bring that 1:20 ratio down to anything comfortable. That's why we've only ever sent a few robots under 1 ton to Mars. Imagine you need to deliver a 20-ton habitat, 10-ton life support, 5-ton science gear, 3-ton comm system, and food, water, oxygen, medical supplies for hundreds of days. The total mass you need to land on Mars could exceed 40-60 tons. Multiply by the 20 factor, you're talking 800 to 1,000, 200 tons in LEO. Once staging, fine, but staging doesn't help when the entire mass has to land instead of being discarded in space. No, because Mars's atmosphere is still enough to turn you into plasma. Want a bigger parachute? 1% density air doesn't care how big your chute is. Want less retro propulsion? No. You'll impact very decisively. This is the kind of math that makes engineers go bald. And the worst part is Mars isn't trying to be difficult. It just happens to sit exactly between two extremes. Not enough atmosphere to help, enough atmosphere to cause trouble. The Moon has none. Earth has too much. Mars is at the exact dead point. It's like wanting to swim, but the pool is only ankle deep, not deep enough to swim. Just enough water to make you slip and fall. And when you combine all the factors, useless parachutes, mandatory heat shields, fuel-hungry retro propulsion, exponentially growing mass, you understand why landing on Mars is not a harder version of moon landing. It is an entirely different problem, a problem where even if you solve it, the solution is anything but elegant. Mars forces you to face the truth. If you want to put tons of cargo on its surface, you must be willing to pay with dozens of tons in Earth orbit. And that's just the way down. The harder part, going back up, still waits for you ahead. And now, let's suppose, just suppose, that through an extraordinary chain of luck, talent, and persistence, you have managed to bring that tens of tons spacecraft down to the surface of Mars. You beat the 1% density atmosphere, beat the friction heat, beat retro propulsion, beat the mass, fuel mass loop that hates everyone. You touch down safely. Wonderful. You can pop the champagne, take photos, send video back to Earth. But I want you to listen carefully to this. If you think getting to Mars is the hardest part, then you have misunderstood the entire problem. This is the most common psychological mistake humans make, not just in physics, but in every field. We focus on the immediate goal, thinking that once we reach it, everything is done. Getting to Mars sounds epic. It captivates journalists, draws live TV coverage, inspires entire generations. But the universe doesn't care about those romantic moments. The universe doesn't measure success by whether you arrived. It measures by whether you return. And returning is when nature starts leaning back, crossing its arms, and smiling with hidden meaning, as if to say, okay, I let you set foot here. Now let's see if you really understand the problem. When you land on Mars, you have completed the easiest part of the mission. And I say this completely seriously. To see why, try flipping your intuition. On Earth, when you climb a mountain, the ascent is usually the hard part, and the descent feels easier. Everyone thinks that way. But Mars is not a mountain. Mars is a mathematical abyss covered in beautiful red dust, and underneath lies a chain of physical requirements that make you want to tear your hair out. To go back up from Mars, you need a new rocket. You heard that right. A rocket, not a tiny module like the LEM. Mars's gravity is 6 times stronger than the Moon's. You cannot just jump lightly and escape. And this is when the intuition of getting there means it's done becomes dangerous. Getting to Mars only requires delivering the landed mass to the surface. But to leave Mars, You must carry the fuel for the return trip, and that fuel must be brought from Earth, unless you build an entire chemical factory on Mars to produce it yourself, which we'll discuss later. The fuel to leave Mars is not like the fuel to land. During landing, you are decelerating. During departure, you are accelerating. Acceleration requires far more thrust than deceleration. So right from the start, the return leg demands far more fuel than the fuel used for landing. And that fuel has to travel with you for the entire 8-9-month journey to Mars, surviving radiation, vibrations, micrometeorite impacts, temperature swings of hundreds of degrees. Human intuition hates facing this, but the truth remains. Return fuel is the heaviest and hardest to protect part of the entire mission. Getting there is easy. You just need to decelerate at the right time. Returning is hard. You have to generate entirely new velocity. Some people say, but if we got to Mars, surely we can leave it. But that's the disastrous. If you climb the mountain, you can climb down. Mindset. Descending relies on gravity pulling you. Mars demands that you pull yourself out of it. Those are two completely different problems. And now think about the human spirit in that moment. You stand on the surface of Mars, tens of millions of kilometers from Earth, and realize that to return, you must trust a tiny rocket system, a little aluminum box assembled entirely automatically, with no mechanics, no shipyard, no factory, no overpass, no repair crew, no chance for testing, and especially zero room for failure. Landing fails, you die. Ascent stage fails, you die. Fuel leaks, you die. Software glitch, you die. And this is when you begin to understand why landing is only the easy part of the whole mission. It's hard, but it's the kind of hard humans have faced before. Pressure, heat, vibration, drag. But the departure back from Mars is the kind of hard humanity has never encountered in history. Hard in the mathematical sense, not just the engineering sense. And hard in the mathematical sense cannot be fixed with duct tape and a prayer like the funny stories from Apollo 13. The simple and brutal truth is reaching Mars only proves you can fall into its gravity. Well, leaving Mars proves you understand physics deeply enough to beat it again. And with all current numbers, nature is speaking very clearly. I allowed you to come here, but to get back, you must be far smarter. Departure from Mars, the final step, but also the most brutal one in the entire journey, where nature looks you straight in the eye and says, to leave the surface of Mars and reach orbit, you need to achieve an escape velocity of about 5 kilometers, much smaller than Earth's 11.2 kilometers per s. Yes, but don't let that number fool you. It's small in the way a lion cub can still bite your wrist clean through. On Earth we have launch pads, fuel factories, transportation roads, cryogenic storage systems, teams of engineers, mechanics, hundreds of tons of logistical equipment, everything that allows a rocket not just to fly, but to be maintained, inspected, assembled, tested. Mars has none of that. No launch pad, no mechanics, no cranes, no oxidizer plant, no inspection station, no one to call, no Amazon delivery, no rescue. You have to launch from a place with zero infrastructure, and worse, all the fuel you need for that ascent burn must be brought from Earth, transported 55 million kilometers through vacuum, landed safely without exploding, stored cold for over 500 days, on a planet where temperatures swing from 20 degrees Celsius down to below minus 120 degrees Celsius, then crammed into a tiny rocket and hoped to work perfectly on its one and only ignition. That's the best case scenario. Now let's talk about what gives engineers the biggest headaches: the mass multiplier, the merciless chain of mass multiplication. Imagine you need 30 tons of fuel to get the ship off Mars. Fine. But to deliver those 30 tons of fuel to the Mars surface, you need at least 300, 600 tons in Earth orbit. Because as we've said, the ratio is roughly 120 for payload delivered to the surface. But to get 600 tons off Earth's surface, you need a monster many times larger than Saturn V. Then when you try to build that monster, you realize it's too big to land or even assemble. You have to break it into multiple launches, then assemble them in orbit, and each step in that chain creates a new mass multiplier. It's the physical embodiment of the joke I love telling students. We carry fuel to carry fuel to carry fuel, and Mars is the planetary scale realization of that joke. An ordinary person might think, just carry more fuel then. What's the big deal? But every kilogram of fuel to leave Mars is a kilogram that had to be brought from Earth to Mars, and every kilogram to bring it from Earth to Mars requires many more kilograms to get it to LEO, and every kilogram to get it to LEO requires still more to get it through the atmosphere and out of Earth's gravity. This loop multiplies until the numbers become technically meaningless. This isn't a rocket building problem. It's a mathematics problem. You can build a 150-meter, 200-meter, 300-meter rocket, but if the equation says no, no one on Earth can bend it. And then there's one more detail. Few like to mention. The rocket leaving Mars has to be absolutely perfect, because you cannot test it on Mars before using it. On Earth, a rocket is tested dozens, hundreds of times, sometimes exploding like fireworks, but no problem. People watch the live stream, tweet a few jokes, and install a new one the next day. On Mars, if it explodes, you die. No spare parts warehouse, no repair station, no engineering team, no retry, no one bringing you a new wrench, no engineer running over to tap a sensor and say, yeah, this is loose, tighten it, and we're good. Every joint, every pipe, every cryogenic valve, every transistor must survive radiation, thermal cycling, fine iron oxide dust, landing vibrations, and still function flawlessly after more than 500 days untouched. And you have to do all that in an environment where a single small mistake can ruin a multi-year mission and kill the entire crew. Try imagining you have a car and you have to drive at 55 million kilometers to a place with no mechanics, then leave it outside for 500 days. No starting, no warm-up, no checks, no maintenance, only to wake up one morning and demand it take you another 55 million kilometers, and you have to survive. No one would believe that car would make it. But with Mars, we're asking a rocket to do exactly that, at a complexity thousands of times higher. And this is the part many don't want to hear, but need to hear. To leave Mars, you don't just need engines. You need a mathematical condition that current technology cannot provide. Mars forces you to confront the fundamental limit of carrying your own fuel. And that limit isn't engineering. It's the logarithm. You can be smart, hard-working, persistent, creative, have a massive budget. But when the problem is carry more fuel to carry the fuel, the only answer the equation gives you is no. Mars is where nature says no. Not because it's cruel, but because every small mathematical error becomes an abyss, and you cannot negotiate with an abyss. You can only avoid it if you're smart enough to spot it before you step in. 35 tons of fuel for a ship that weighs only about 10 tons already sounds absurd. But what makes it a true nightmare is that all 35 tons must be transported from Earth down to the Mars surface before it can burn a single drop. This isn't exaggeration. This is how mathematics answers when you ask how much fuel is needed to leave a planet with 38% of Earth's gravity, but no infrastructure. If you want to get a vehicle with a total takeoff mass of 10 tons into Mars orbit, you have to allocate about 80% of its initial mass to fuel. because that's the mass ratio required to achieve roughly 4.3 kilometers per sec delta V, enough to get you into a stable orbit without falling back or flying off. That means your 10-ton ship has only 2 tons left for structure, equipment, engines, control systems, computers, wiring, sensors, load-bearing frame, minimal life support, and everything else. You might ask, why 80%? Because that's how the rocket equation works. A methane, oxygen engine has an exhaust velocity around 3.5 kilometers per s, and to reach 5 kilometers per s delta V, M0/M1 must fall somewhere between 4 and 6. That means if the dry part of the ship weighs 2 tons, total takeoff mass must be in the 8-12 ton range. That's 6-10 tons of fuel minimum. But that's in an ideal model. No Mars gravity losses in the first seconds, no safety margins, no losses, no boil-off. When you plug in real parameters, temperatures from minus 120 degrees Celsius to 20 degrees Celsius, gradual degradation of oxygen and methane purity, cryogenic lines and valves aging, boil-off rates, unstable pressure, the number jumps to 35 tons. Mars doesn't let you carry a single drop of extra fuel because every drop is weight you have to land. And to land it, you need more fuel for retropropulsion. And to carry retropropulsion fuel, you need to launch more mass from Earth to LEO. And to launch more mass from LEO, you need more fuel to push that fuel out of Earth's gravity. This is the famous mass multiplier chain that keeps engineers awake and makes politicians pretend not to see. 35 tons of fuel is no problem when you're on Earth. You just need tank trucks, highways, cargo ships, cranes, storage tanks. But on Mars, those 35 tons are like an elephant abandoned in the desert. No one can rescue it. To deliver 35 tons of fuel to the Mars surface, you need at least 700 tons in Earth orbit, based on the average 1:20 ratio. 700 tons in LEO means you're demanding roughly 8-10 times the launch capability of Saturn V, or dozens of launches from modern heavy rockets. But even if you manage that, you still haven't beaten the problem, because those 35 tons of fuel don't just need to be delivered to Mars. They need to be loaded into a ship that must operate perfectly after being left exposed outside for over 500 days. No maintenance station, no thermal test chamber, no team of 20 engineers poring over every detail before launch. You might ask, why not carry the fuel frozen for storage? Because methane and oxygen aren't popsicles. They need to be kept at cryogenic temperatures, and cryogenic systems on Mars can't run as simply as your home fridge. A daily boil-off rate of even 0.1% will ruin the entire calculation after a few hundred days. Then you have to think about Mars dust, a fine iron oxide powder, like talc, that gets into every crevice, every joint, every mechanism. Valves, pumps, lines, sensors, all of them cannot jam even once. And the funniest part is none of that is even the worst part. The worst part is those 35 tons of fuel are carried just to get 10 tons of mass off one planet. This is something human intuition refuses to accept. We're used to cars, buses, airplanes, things that can carry tons of metal with just a few hundred kilograms of fuel. But those are vehicles that rely on lift, on air, on friction, on an environment where nature lets you lean on it. In vacuum, air doesn't help you. No free lift, no temporary landing spots, no using the terrain, no light out, heavy back, no miracles, only the rocket equation. And the rocket equation doesn't soften. It doesn't care that you successfully reached Mars. It doesn't care that you have a beautiful ship, skilled astronauts, fancy software. It only looks at M0/M1 and says want to fly, pay the exact price. And if the price to get 10 tons into Mars orbit is 35 tons of fuel, that's a number no prayer can change. This is the essence of the Mars return problem. It's not that technology isn't strong enough. It's that the mathematics itself doesn't favor you, and you cannot rewrite mathematics with dreams or budgets. The universe doesn't negotiate. Nature doesn't compromise. And the rocket equation, like every other law of physics, continues to do its job, reminding us that not every problem is written for humans to solve. Round-trip delta V is where the full cruelty of mathematics is laid bare most clearly, and also where you realize that Mars isn't just a little farther, but is an entirely different order of magnitude from the Moon. When we talk about Apollo, the total delta V for the entire mission, from leaving Earth, entering orbit, TLI, mid-course corrections, landing, liftoff from the Moon, and return, fell around 16 kilometers per s. That number sat right in the range Saturn V could deliver if you accepted multi-stage staging, continuous mass shedding, and optimization down to the kilogram. But Mars isn't that polite. For a round trip to Mars, you need a total delta V somewhere in the 18-22 kilometers per s range, depending on launch windows, orbital deviations, and return profiles. At first glance, a 3-6 kilometers per s difference doesn't seem huge, like accelerating from 60 kilometers per h to 90 kilometers per h. But delta V is never ordinary speed. Delta V is energy calculated in an environment with no support, no air, no lift, no brakes, and especially no free fuel. Every bit of delta V must be purchased with mass, and every piece of mass must be purchased with other mass to carry it. When you increase a mission's total required delta V by 20-30%, you don't increase total mass by 20-30%. You can make total mass increase 300-400% or more. This is the absolute power of the logarithm in the rocket equation. In the equation log equals sign V, quotient ln, m0/m1, delta V is on the left side, but mass ratio is what decides everything. If you want to increase tau V by a few kilometers, m0/m1 has to grow exponentially. And if you're working with chemical engines whose exhaust velocity is only about 4.5 kilometers per s, you're pushed into a region where mass ratio becomes insane. With 15 kilometers per s, Saturn V could still manage with staging. But when you need 18, 20, 22 kilometers per s, you enter the cannot carry enough fuel zone, where even doubling, tripling, or quintupling rocket size still gets defeated by mass ratio without effort. To get an intuitive sense of why 3-6 kilometers per s causes such catastrophe, look at an example. You're trying to throw a ball to the top of a building. If the building is 10 meters tall, you can throw relatively gently. If it's 12 meters, 20% taller, you don't throw 20% harder. You have to throw much harder because kinetic energy scales with velocity squared. That's how classical mechanics works. But for rockets, the problem is far worse. When you increase the requirement from 15 kilometers per s to 20 kilometers per s, you don't just need more thrust. You need more fuel to produce that thrust, more structure to hold the fuel, more framing to resist vibration, more thermal control systems. And all of it makes the ship heavier, requiring even more fuel. A snowball rolling downhill can cause trouble, but mass ratio is a snowball rolling down the s-slope of the logarithm. It doesn't stop, it accelerates, and it crushes every design. In practice, analyses from leading research agencies show that a 3-6 kilometers per s difference can make the total launch mass required for a Mars mission 3 to 4 times larger than for a Moon mission. even under the most optimistic conditions. If Apollo needed approximately 3,000 tons to reach the moon, a Mars mission in a bring fuel from Earth configuration could need 10,000, 12,000 tons, or worse if you include multi-year life support mass. And that number doesn't come from pessimism. It comes from the reality that as total delta V increases, mass escalates exponentially with no stopping point. This is where the problem leaves the world of engineering and enters pure mathematics. You cannot solve it with slightly stronger engines, slightly bigger tanks, or slightly lighter systems, because no matter how much you optimize, the logarithm looks at you coldly and says no. The problem isn't that Mars is too far. The problem is that the round-trip total delta V sits just on the other side of the feasibility boundary. If you cannot reduce mass or increase exhaust velocity exponentially, which current technology cannot do, the problem retains its logarithmic slope that makes every attempt to launch bigger rockets meaningless. When you understand that delta V alone makes a Mars mission grow exponentially enormous, you begin to realize a far more terrifying consequence. The spacecraft needed to bring humans back from Mars must be larger than anything we have ever built, even larger than the ISS, the largest space structure humanity has ever assembled in orbit. It sounds like exaggeration, but let mathematics guide you step by step, because it has no reason to lie. Start with the simplest requirement: to get a crew of 4, 6 people off the Mars surface and back to Earth. You need a ship strong enough to achieve about 6-7 kilometers per s delta V for the ascent, plus about 2-3 kilometers per s for orbital adjustments, plus a few more kilometers for the return transit and Earth re-entry. The entire round trip demands 18-22 kilometers per s, and as we've seen, that's the delta V region, where mass ratio inflates like an overinflated soap bubble. If you want to bring back 20-30 tons of payload, including habitat module, living quarters, remaining food, water recycling systems, science gear, basic radiation shielding, and a shielded cabin to survive the 9-month return flight, then the dry mass of the ship alone is already 20-30 tons. But 20-30 tons is just the dry part. When you want to achieve 6-7 kilometers per s delta V from the Mars surface using chemical engines, you need at least 80-85% of total mass to be fuel. That pushes minimum total mass to around 120-150 tons just for the Mars departure stage. But that's only the part leaving Mars. When you add the fuel needed for the return journey, propellant for course corrections, safety reserves, thermal protection systems, plus minimal shielding to keep the crew from becoming DNA barbecued under cosmic radiation, total mass easily exceeds 200-300 tons. And that's the minimum in an ideal model. No fuel leaks, no temperature deviations, no material degradation, no cryogenic losses, no software errors, no emergencies requiring unplanned delta V. Reality is always at least 30-50% worse than theory. When you plug in real parameters, the total mass of the Mars return spacecraft, the one that must be in Mars orbit or assembled in Earth orbit before departure, approaches 400-600 tons, and in many traditional configurations, it even hits 800-1,000 tons. For comparison, the ISS weighs about 420 tons after more than a decade of continuous assembly, using over 30 space shuttle flights and multiple heavy rockets, and that was assembled right next to Earth. Assembling 400 kilometers away from Earth is not the same as assembling 55 million kilometers away. On the ISS, everything is within reach. If you're missing a wrench, you can send it on Soyuz or Dragon. If there's a technical fault, you can swap modules or send mechanics up to fix it. If an astronaut gets sick, you can bring them home in hours. On Mars, no deliveries, no chance to send spare parts, no repair crew, no backup. You cannot say, oh, we forgot extra CO filters, send more up. The universe just shrugs. No one comes. So that 400, 800-ton ship doesn't just need to be big. It needs to be absolutely self-sufficient, absolutely durable, absolutely stable, and able to endure brutal conditions for years on end. And this is the part many don't understand. We have never built a spacecraft weighing 400, 800 tons, capable of fully autonomous operation. The ISS is not a ship. It doesn't move. It doesn't need landing gear. It doesn't need a heat shield. It doesn't store fuel for 20, 30 kilometers per S delta V. It isn't a closed environment that recycles resources for years without resupply. If the ISS had to fly itself to Mars, it would disintegrate in the first hour from engine acceleration and vibration stresses. We have never constructed any space structure with the mechanical properties, mass, and reliability required for Mars return. All of humanity's spacecraft building experience, from Apollo to Shuttle to Orion, has been at scales of a few tons to a few dozen tons. When you scale to hundreds of tons, the physics of vibration, resonance, load transfer, cooling, radiation protection, and thermal stability enter unexplored territory. This isn't a matter of just make a bigger rocket. This is humanity has never stepped into this class of mathematics before. I once told my students, the universe doesn't care that we lack experience. If you throw a 600-ton ship into space without the ability to withstand millimeter-scale vibrations, it will shake itself to pieces. If you don't have proper shielding, the crew will absorb sieverts of radiation during the journey, whether you like it or not. If you don't have enough delta V, you can't return. If you try to save, you miss orbit and die. The universe doesn't say, oh, this is your first time. Let me lower the requirements a bit. It's not a lenient teacher. It's like a multiple choice test, where every wrong answer is absolute zero, and you get no retakes. And when you look at that 400, 800-ton number, you understand why Mars return cannot rely on intuition or technological miracles like Apollo. Apollo 1, because the problem was small and fit perfectly. Mars loses because the problem balloons exponentially to the point where we don't even know where to begin. The ship to return from Mars must be twice the size of the ISS, but function like Apollo. We have never done anything like it, but the universe doesn't care. It just presents the problem and waits to see if you can solve it. The orbit between Earth and Mars isn't two highways where you can catch a ride anytime. They're two vehicles orbiting the sun at different speeds, and you can only jump from one to the other when they're in exactly the right geometric alignment, called a transfer window. And the first thing you have to accept is the universe doesn't care about your schedule. It doesn't wait for you, doesn't extend deadlines, has no delayed flights, no extra trips. The transfer window to go from Earth to Mars opens only once every 26 months. And if you miss that window, you can't say, okay, I'll just fly a week late. There is no week late. You have to wait more than another 2 years. And in the language of space travel, that level of inconvenience is equivalent to missing a bus and the next one coming next year. This creates an extremely cruel consequence. If you successfully reach Mars, you have to stay there for about 500 days before you can leave. You cannot return immediately, no matter how homesick you are, no matter how perfect your ship is, no matter how much the crew's morale plummets. There is no early return, no catch the next flight, no temporarily leave the mission. You arrive when the orbits demand it, and you leave when the orbits allow it, not when you want to. This is where human intuition completely fails. On Earth, all our survival behavior is tied to the idea that if things get too bad, we can always retreat. But on Mars, retreat does not exist. You cannot call for a rescue ship. You cannot scramble a shuttle. You cannot tough it out a couple more days and go home. You are locked into the solar system's timetable, and it doesn't change for anyone. You arrive on Mars in the month you left Earth, but you can only leave Mars when Earth and Mars are again aligned in the right orbital positions for your return burn. And suppose you arrive in April of some year, you have to wait until August of the following year to leave. 500 days. More than a year and a half, living on a planet with toxic air, high radiation, all kinds of fine dust, temperatures that can drop to minus 120 degrees Celsius at night, and no emergency exit. This isn't a long vacation. This is an absolute physical constraint, and this very constraint is the psychological factor that many people dangerously underestimate. When you know you're trapped in a space tens of millions of kilometers from Earth with a small group of teammates inside a habitat the size of a few stacked shipping containers, your mind starts doing very strange things. Humans did not evolve to live in an environment where every small error can kill everyone. Humans did not evolve to live in an environment with no go outside for a walk to relieve stress. Humans did not evolve to look at an endless red horizon every day and know there is no one out there. You're stuck with your crewmates, and they're stuck with you. No shift changes, no time off, no social outings, no leaving the mission, no direct intervention from psychologists. Every conversation has a delay of a few minutes to tens of minutes. If you argue with someone, trust me, going for a walk to cool off is not an option on Mars. And throughout those 500 days, you also have to face the reality that even if you survive until the launch window opens, you still have to perform an ascent whose safety depends on a tiny metal structure that has endured hundreds of days of radiation, fine dust, fluctuating temperatures, vibrations from landing, and complete lack of maintenance. That is psychological pressure no simulation on Earth can replicate. Understanding orbits isn't just understanding geometry and time. It's also understanding human endurance. The universe puts you on a stricter schedule than any tough professor, and if you don't comply, you don't get to return. Not because NASA doesn't want to save you, but because physics doesn't allow it. The transfer window is a law of celestial bodies, not a suggestion. The universe doesn't say, I understand you're very busy. I'll open the window a little longer. It just keeps turning, cold and steady, while you count every day on a distant red planet, waiting for the one and only moment when Earth and Mars say, okay, if you want to go home, now is the time. Cosmic radiation is something many people hear and think, oh, it's just radiation. We've dealt with radiation in medicine, in reactors, in research. But cosmic rays are not the cute kind of radiation you encounter in hospitals. They are high-energy particles, accelerated to near the speed of light, fired straight at you like subatomic bullets, and Mars has no shield to protect you from them. Earth is lucky to have a magnetosphere, a giant magnetic bubble so large it bends the entire stream of high-energy particles from the sun and supernovae, keeping them from hitting your DNA. You're living thanks to that invisible bubble, even if you never thank it every day. But Mars once had a magnetic field, but it died billions of years ago. Now it sits naked like a tennis ball in the middle of a cosmic ray shooting range. Mars's atmosphere is too thin to absorb radiation. There's no magnetic field, and the surface receives showers of energetic particles that, if visible to the naked eye, would probably make you run straight back to Earth and hug the magnetosphere like your mother. Cosmic rays don't just make you sick, they shred your DNA. Imagine you're a book, and cosmic rays are a naughty child, walking around tearing out pages one by one, then tossing them into a blender. That's the level of destruction. A single cosmic ray can pierce through the spacecraft hull, through a spacesuit, through a few centimeters of aluminum and still have enough energy to snap a DNA strand in two inside a cell. And unfortunately for you, human cells are not great at repairing this kind of damage. The consequences don't come immediately. Cosmic rays are like a delayed gift. You see nothing at first, but a few years later, you realize the gift was cancer. And now let's talk about shielding, the layer humans think can solve every problem to block cosmic rays effectively. You don't need a few millimeters of metal. You need several meters of material. Water can be used. Polyethylene can be used. Regolith can be used. But you cannot carry several meters of material wrapped around the ship as if you're building a flying bunker in space. You might think, just a few meters, what's the big deal? But remember the rocket equation. If every meter of shielding for 1 square meter of surface weighs tons, and you need to cover a ship with 40-60 square meters of area, you're talking about 200-500 tons of shielding material. And that's just to reduce radiation to the level of not dying immediately. If you want to protect the crew during 500 days on Mars plus 9 months outbound and 9 months return, nearly 3 years total, you'll need even more. This leads to the conclusion no one wants to hear, but cannot avoid. Humans do not have a turtle shell. A turtle has a shell tens of centimeters thick, and if you sent a turtle into deep space, it might survive longer than you think. But humans do not. We have skin. Skin is great at holding water, blocking dust, regulating temperature, but it doesn't stop cosmic rays. On Earth you don't face this because the magnetosphere and atmosphere do all the heavy lifting. You can sit outside for hours and your DNA stays pretty okay. But in deep space, where radiation comes from every direction with no natural infrastructure to protect you, your body becomes an open target. If you want a visual, imagine I take you into a lab and put a piece of film in front of you. Then I fire a few low-energy electrons at it. You'll see a few small bright spots. But if I use cosmic rays, you'll see long, thick, violent streaks, as if someone took a razor blade and slashed across the film. That's exactly what happens to your DNA on a journey to Mars. We haven't failed to measure it. Sensors on missions like Curiosity, Maven, TGO, all report radiation levels many times above human safety thresholds. Some simulations show the crew could accumulate a lifetime cancer risk increase of over 20-30%, even under optimal shielding conditions. And what makes me laugh bitterly is this: we can build ships 100 times stronger, make engines twice as efficient, calculate orbits to the millisecond, but cosmic rays still look at us and say, "Cute, but you're made of meat." This doesn't mean a Mars mission is impossible. It just means humans have to accept a level of biological risk we've never accepted before. An astronaut who goes to Mars may return in significantly worse health, with DNA damage that current science cannot fully repair. Not because technology is weak, but because nature designed cosmic rays stronger than any shield we can afford to carry. And that's why I always tell my students, if you want to go to Mars, you must bring the mind of a physicist, the heart of an explorer, and the recklessness of someone without a turtle shell. 6 humans inside a flying metal box in the void is not the romantic image movies like to paint. It is the longest and harshest psychological experiment humanity has ever put itself through. You don't need radiation, meteorites, or engine failure to create disaster. Just time, isolation, a few small misunderstandings, and the human brain will do the rest. The universe doesn't even have to act. You and your crewmates can drive each other insane. On Earth, you don't realize how much you rely on community, city noise, wind, trees, sky, going for a walk, meeting strangers, morning coffee, stepping out of the room when you're annoyed. But on the journey to Mars, and the 500 days spent there, your entire world shrinks to a few dozen square meters. 6 people, an alien planet, a metal box, and one non-negotiable physical truth. No one can go anywhere. The mental atmosphere in such an environment is not as light as you think. The living space isn't just cramped. It's compressed by transcendent responsibility. No one comes to help if you screw up. No fix it tomorrow. No, I'm taking a week off. Every day you wake up, you face a project whose failure means everyone dies. Every word, every decision, every minor disagreement piles onto this baseline pressure and can become the spark. And the funny thing is, the human psyche isn't designed for perfection. Our brains make mistakes. We get irritated, tired, cranky, sleepy, think unclearly, misinterpret signals, mishear words, overimagine, worry irrationally. That's harmless on Earth. But on Mars, a small mistake equals a major catastrophe. Simple example, you forget to lock a gas valve. On Earth, your boss yells at you. On Mars, you could depressurize the cabin and kill everyone. You skip an important measurement because you're exhausted. On Earth, you rewrite the report. On Mars, you might miss a warning signal for a power failure and cause total loss of heating at night. A few hours later, you and your crew become ice statues. And then we have to talk about signal delay, the thing many think is just inconvenient, but actually shatters the entire psychological support structure humans are used to relying on. When you're a few million kilometers from Earth, the delay is just seconds, but at 100 million kilometers, it can be 20-25 minutes each way. That means if you have an emergency and say, Houston, we have a problem, it takes 40-50 minutes for Earth to hear and respond. By then your problem may already be a national funeral. You cannot talk to family in real time, cannot ask experts for advice, cannot comfort each other by hearing voices. You only have the sound of ventilation fans, footsteps, the CO2 scrubber, cycling, and your own thoughts. If 2 people misunderstand each other, you cannot explain right away. Delay makes every conflict longer, more simmering, more toxic. A casual remark can turn into a slow-burning ember in someone's mind for tens of minutes before they realize you meant nothing by it. In a normal environment, silence is peaceful. In space, silence is the echo of absolute isolation. Simulations like Mars 500, Hawaii East Seas, NEC in Russia, all show the same truth. Humans are not suited for long-term isolation, and stress quickly turns to chaos without a broad social support system like on Earth. But inside a box in space, your support system consists of exactly 5 other people, people you cannot avoid, cannot replace, cannot walk away from. And all of this happens in an environment where every decision affects lives. You're not just living together, you're riding together on a gigantic rocket of responsibility, and that pressure compresses the human psyche to the point where any conflict can become a real threat. You don't need the universe to kill you. Humans are already equipped to do it to themselves. The universe just has to close the door and let you and your crewmates deal with each other. And if you think that's pessimistic, remember that the entire aerospace industry spent decades just figuring out how to make 3 people live together on the ISS for a few months without hating each other. Now increase the time to 3 years, shrink the living space, cut off psychological support, ramp up lethal pressure, and put them on a lifeless planet. 6 people in a box isn't an engineering mission. It's a philosophical question about the resilience of the human species. The universe just watches and laughs. Let's see how you handle each other. And then after all the psychological issues, radiation orbits, living conditions, and spacecraft structure, we return to the first and final enemy of every Mars return dream, fuel. You might think we've talked about it enough, but the mass cascade isn't something you handle and forget. It comes back like a mathematical demon, clinging stubbornly to every phase of the mission, from the moment you ignite engines, to leave Earth, until you burn the last drop, to decelerate on return. When you stand on the Mars surface and look up at the pale red sky, you'll realize the most important question isn't can we survive, but do we have enough fuel to leave here? And that's a question you shouldn't ask when you've already arrived. It must be answered back on Earth. The problem here isn't that fuel is rare or expensive. The problem is that fuel has mass, and that mass obeys the Tsiolkovsky equation, which I always see as a test you cannot cheat on. If you want to deliver 1 kilogram of fuel to Mars, you need to bring about 20 kilograms to LEO. If you want to deliver 20 kilograms of fuel to Mars, you need to launch 400 kilograms to LEO. If you want to deliver 35 tons to Mars, you need 700 tons in LEO. If you want to deliver 60 tons to Mars, you need over 1,200 tons. And that's just to get the fuel to the surface, before accounting for the fuel needed to leave Mars, or just orbit and decelerate back to Earth. Fuel never stands still. It creates a cascade, a chain of mass multiplication that grows so fast, a small calculation error can jump the entire mission from feasible to cannot even launch. This is the essence of mass cascade. Every kilogram you add at the end of the mission multiplies throughout the entire chain. It's like adding a small brick to the top, but the foundation has to expand threefold to support it. It's unfair, but the universe never promised fairness. And this is precisely why fuel becomes the greatest enemy of Mars return. It isn't propellant, it's burden. It doesn't help you, it binds you. You cannot reduce it, because a little short means death. You cannot carry too much, because the mass cascade will kill you before Mars does. You cannot store it easily, because cryogenic propellants boil off over time. You cannot rely on it to be safer, because more fuel means heavier ship, higher risk. Carrying fuel is like carrying water across an infinite desert. The more you carry, the more you need to carry the water itself. And if you think that's an exaggerated metaphor, try solving this problem. You want to leave Mars and return to Earth. You need about 40 tons of fuel. But to land 40 tons on Mars, you need 800 tons in LEO. But to get 800 tons to LEO, you need to launch several thousand tons from the ground, meaning dozens of launches from super heavy rockets that don't yet exist. And that's without counting system redundancy, margins, shielding, oxygen, water, food, backup thrusters, and all the miscellaneous items. That isn't a plan. That's lyric poetry, with dreams far exceeding engineering. And this is the moment you must admit, one thing, carrying fuel, is not a viable option. It's like trying to build a skyscraper by piling more floors onto a foundation that's already cracking. Each new floor creates more cracks. You can add a little, add a bit more, but eventually the whole structure collapses. For Mars return, fuel is the heaviest floor of that building, and the foundation, mass ratio, cannot bear it. I always tell my students, the universe doesn't care how much fuel you need. It only cares how much you can carry without killing yourself. And when you look at that cascade, you see that fuel isn't just the problem, it is the problem. Mars doesn't kill you with radiation, doesn't kill you with cold, doesn't kill you with isolation, at least not right away. Mars kills you with mathematics, by forcing you to carry the one thing you cannot carry, the very fuel you depend on to return. ISRU, in situ resource utilization, sounds very fancy, very futuristic, very let Mars help us. But when you peel back that glamorous layer and look straight at the physics and chemistry, you'll see that ISRU is not the magical solution many people hope for. It's a gamble, and the price of losing this gamble is the lives of the crew. The idea of ISRU is beautiful. Instead of hauling 30-40 tons of fuel from Earth to Mars, produce the fuel right on Mars. This is the only way to break the mass cascade we just exposed in the previous part. There is no other choice. The essence of ISRU relies on two available resources: Mars's atmosphere, which is about 95% CO hard, and subsurface water ice. From CO hard, you can extract O5 via oxide electrolysis or other oxygen release processes. From water ice, you can electrolyze to produce acid and O5. Then you run acid and CO hard through the Sabatier reaction, a chemical reaction so simple I can write it on the blackboard in a Caltech classroom. CO hard plus 4H hard plus 2H hard. The water is re-electrolyzed into H hard and O5, and CO hard and O5 become rocket propellant. Sounds reasonable. Sounds very clean. Sounds like a 10th grade chemistry exam question you could solve in 15 minutes. But that's only the story on paper. And paper never gets damaged by radiation, never gets clogged by Mars dust in the filters, never cracks its pipes at minus 120 degrees Celsius, never shatters pumps from vibration, never gets paralyzed by a lack of engineers. In reality, we have never operated a full Sabatier electrolysis plant anywhere outside Earth, and certainly never operated it with the goal of producing 35 tons of propellant in an environment more remote than any place humans have ever set foot. In labs, we can crack CO hard, extract O5, electrolyze ice, produce methane. We can do all those steps with suitcase-sized equipment. But for a Mars return mission, you don't need a suitcase. You need a complete chemical plant running continuously for 300, 400 days on a cold, dusty, barren planet where every small error has a 100% chance of leading to death if not fixed immediately. And then there's the scale problem, the one every engineer fears. This works great in the laboratory. That sentence is a curse. Scale it up 1,000 times and everything breaks. Reaction kinetics change. Efficiency drops. Catalysts die faster. Pumps vibrate excessively. Heat exchangers go out of phase. Valves jam from fine iron oxide dust. Cryogenic heating systems can't maintain temperature. Filters clog. Every small issue at lab scale is an error. At plant scale, it's a catastrophe. An ASRU from Mars has to operate at plant scale, not toy scale. Worse, ASRU must be sent to Mars a year before the crew leaves Earth, and it has to run autonomously. No one to maintain it, no one to repair it, no one standing next to a valve tapping it and saying, yeah, this is a bit loose. It has to run like a Swiss watch in an environment worse than every laboratory on Earth combined, producing enough 30-35 tons of methane, oxygen, storing it safely, and waiting. If it fails in month 2 or 6 or 11, you have no Mars mission. You cannot send a technician up to fix it. You cannot reboot the system remotely. You cannot replace a pump. You cannot investigate the failure. You have only one choice: abort the mission. If you don't abort, you send humans to Mars only for them to discover that their return ticket burned up in the Sabatier reactor months earlier. And do you know what the cruelest part is? ISRU doesn't just have to work perfectly during production. It also has to work perfectly during storage and cryogenic methane. Oxygen is not easy to store. Methane boils off. Oxygen boils off. And if the CH air to O ratio drifts by even a few percent, the mixture is no longer optimal for the engines. Pressure changes, and you may create a floating bomb on the Mars surface. Storing cryogenics for 500 days in the Mars environment is not a small challenge. It's one of the highest tiers of thermal and materials engineering. And remember, if the mixture loses just 10% to boil off, you lose delta V. Lose delta V, and you don't have enough velocity to leave Mars. Not enough velocity means you die. ISRU is required to work perfectly on one planet at a capacity no one has ever tried, over a time frame, with no supervision, with the consequence of a small mistake being the entire crew stranded forever. And that's when I, if standing in class, would smile lightly and tell the students, this is the only experiment in the history of science with no test runs. Either you get it right the first time, or there is no second time. Mars is not a place where you learn from mistakes. Mars is a place where mistakes end all lessons. ISRU may be the best solution we have, but it is also a reminder that the universe does not compromise, does not give second chances, and never signs a test permit for you. The challenges we've discussed, delta V, mass cascade, ISRU, radiation, psychology orbits, have already been enough to keep any space engineer awake at night. But the scariest part is that's not the entire problem. A true Mars return mission is like having to pass the 3 hardest exams of your life, not sequentially, but simultaneously, landing a massive payload on a planet with the worst atmosphere in the solar system, surviving 500 days in an environment that allows no errors, and finally re-entering Earth's atmosphere at 12 kilometers per s, faster than any human has ever returned. Each one is hard. Together they become a chorus of trouble. Start with landing, the thing Hollywood loves, turning into a romantic moment, with the ship descending to Mars amid dramatic music. But real landing is the problem Mars loves using to teach engineers never to get overconfident too early. You have to decelerate from about 20,000 kilometers per h down to walking speed in just a few minutes in a 1% density atmosphere. Not thick enough for parachutes to work well, thick enough to burn up the ship, and too thin for stable force transfer. That forces you to combine heat shield, parachute, retro propulsion, 3 systems that don't like cooperating, into a deadly dance where even half a second off rhythm creates a new crater on the Mars surface. When you've conquered landing, you're not allowed to breathe a sigh of relief. You're only allowed to move on to the second exam, surviving 500 days, not 5 days, not 50, but more than a year and a half inside a metal box, tens of millions of kilometers from Earth, where every small mistake can kill the whole team. Your life support systems must run continuously for 12,000 hours without a major failure. CO5 scrubbers must work. Water recycling must be precise. Heaters must survive nights down to minus 120 degrees Celsius. And power must run non-stop. If you think a few-hour blackout on Earth is bad, try imagining one on Mars. Batteries die, heaters shut off, cabin pressure starts dropping, and there's no one out there to call. When you survive the first few months, you face gradually accumulating radiation into your DNA, prolonged isolation, signal delays that dilute every conversation, a cabin too small, constant ambient noise from fans and pumps you can't turn off. And if you think sitting still for 500 days is boring, remember you still have to operate a habitat, maintain electrical systems, environmental controls, check valves, monitor batteries, fix every emerging fault, and do all of it knowing there are no spare parts. A failed pump on Earth is a minor incident. A failed pump on Mars could be the final chapter in your book. And then after 500 days, you reach the 3rd exam, leaving Mars and returning to Earth, the culmination of the chain of challenges, where every accumulated error becomes the final demon you must face. You must perform a perfect launch in an environment with no engineers, no support, no backup. You must get the ship into Mars orbit, perform the return burn, make orbital adjustments over another 9 months, avoid radiation, avoid trajectory errors, ensure equipment works perfectly after 3 years of wear. And then this is the part very few people think about. You must re-enter Earth's atmosphere at about 12 kilometers per s, nearly 40% faster than Apollo. That number isn't just a little more. It's the difference between entering the atmosphere like a pebble and entering like a meteor. NASA has simulated Mars, return re-entry, and the only way not to burn into plasma is to have a larger, tougher heat shield that withstands higher heat flux than anything humans have ever built. And if you come in too steep, you vaporize. Too shallow, you skip off the atmosphere like a marble off a table and go back into orbit, where you die from oxygen depletion. Even if you hit the exact angle, speed, and mass, you still endure extreme G-forces and temperatures that can incinerate even the best heat-resistant ceramics. Re-entry from LEO is a challenge. From the moon, it's hard. From Mars, it's an exam where you cannot afford to miss a single stroke of the pen. But the story doesn't end there. You have to consider the possibility that all these risks stack together. A 3-year mission never encounters just one problem. It encounters dozens. A small error in the air filtration system months earlier can stress the crew. Stress causes mistakes in maintenance procedures. Mistakes cause electrical equipment failure during a dust storm. Dust storm weakens batteries. Weak batteries shut off heaters at midnight. The team spends energy repairing. Fatigue leads to errors during launch. Slight launch deviation burns too much fuel. Insufficient fuel makes re-entry more dangerous. That chain of risks doesn't operate independently. They coordinate like a chorus of trouble, each error a musician, and Mars the conductor who never forgives a wrong note. This is not a mission for bigger technology or bigger budgets. This is a mission where every factor must be perfect, and perfect for 3 continuous years. Just one thing wrong, just one, and the entire journey collapses. The universe doesn't need to do anything to stop you. It just stands there, watching you wrestle with hundreds of brutal variables, and waits to see whether you give up before or after mathematics speaks. Why is returning from Mars the harshest test nature has ever set for humanity? Not because Mars is malicious, not because it's distant, not because there's some conspiracy hidden behind its thin atmosphere. The real reason lies in the fact that nature is always absolutely honest, and honest to the point of cruelty. It doesn't negotiate, doesn't soften, doesn't flex with the budget, doesn't bow to ambition, and certainly doesn't grant exceptions to those who want to return from another planet. Nature says only one thing: want to come back. Pay the exact price according to the equation. No more, no less. And to understand that price, you only need to look back at the entire line of reasoning we've walked through from the beginning to now. We started by smashing the mistaken intuition that Mars is just a little farther than the moon. No, the distance doesn't just increase a few times. It increases to the level that distorts every survival requirement you have. 3 days to the moon becomes 9 months to Mars. The ability to turn back, the single greatest safety line in every Apollo mission, becomes absolute zero. On the way to Mars, you're not in a dangerous situation. You're in a no-escape situation. Then we entered the mathematics, delta V, the rocket equation, mass ratio, the logarithm, all things that care nothing for emotion, dreams, or courage. You want a few more km's of velocity. Your mass triples, quadruples. You want more fuel. Carry more fuel. To carry the fuel. To carry the fuel. You want to reduce risk by adding margin. Margin turns into mass. Mass turns into fuel. Fuel turns into heights beyond the capability of any launch pad that has ever existed. And then you look at Saturn V, the wonder of Apollo, and realize it was only a narrow bridge just wide enough to reach the moon, and it cannot be extended to Mars, because Apollo's 16 kilometers per s problem becomes 22 kilometers per s in Mars return, and crosses an entirely new boundary of physics, where everything balloons exponentially. When we dug deeper, Mars kept revealing its fickle nature. Atmosphere too thin to slow you, but thick enough to cause heat. Landing becomes a logically contradictory problem. 1 ton of payload on the surface turns into 20 tons in LEO, wrecking every calculation. Then we went to psychology. 6 humans in a metal box, 20-minute signal delay, no retreat option, no mental support, all dependent on each other, with no one able to escape anyone. In that environment, the universe doesn't need to act. Humans can drive each other insane enough to ruin the mission. Not done yet. Cosmic rays, atomic-level bullets, pierce every shield you can carry. No magnetosphere, no thick atmosphere, no turtle shell, just muscle, DNA, and high-energy particles, carving lines across your genetic book. Then ISRU, the hope many see as the only escape from mass cascade. But ISRU is not magic. It's a chemical plant that must run perfectly for a year before humans arrive, without failing, without vibrating, without clogging, without losing catalyst, without pressure loss, without methane boiling off 10%, without oxygen freezing in the wrong place, because a single small error means the crew arrives to find their return ticket to Earth has already blown away in silence months earlier. And just when you think the list of challenges is full, Mars throws 3 exams at you simultaneously, landing with the highest risk factor in aerospace. 500 days of survival in an environment where any mistake can kill, and re-entry from 12 km fast enough that if you enter at the wrong angle, by just 0.2 degrees, you turn into plasma. That's not one mission. That's a symphony of trouble, each instrument a risk, and Mars the conductor, who always keeps the tempo unforgiving of mistakes. All of this leads you to the only honest conclusion a physicist can give. Mars return is not impossible forever, but it is impossible today. Not because humans are less intelligent, not because technology is slow, but because nature has set requirements we do not yet have the tools to meet. For Mars return to be feasible, we need engines with exhaust velocity many times higher, nuclear thermal or nuclear electric at levels not yet, mature radiation shielding that's effective without weighing hundreds of tons, lighter yet tougher materials, life support systems that can run flawlessly for 3 years, AI strong enough to operate, ASRU without human touch, re-entry vehicles that withstand 12 kilometers per s without heat shields as thick as fortress walls. In short, we need a toolbox of technology that humanity does not yet possess. That doesn't mean Mars return will forever be a fantasy. It only means Mars stands one step beyond the reach of this century's technology, just as the moon stood beyond reach in 1900. No one back then could imagine a 3,000-ton rocket, but 70 years later we did it. Mars return is the same, not never, but not yet. But not yet is not an excuse to underestimate the problem. On the contrary, it's a reminder that nature does not allow cheating. No shortcuts, no chance to retake the test, no emotional exceptions. Want to return from Mars? Nature demands you put the exact number into the equation, and until we have technologies the equation accepts, the universe's answer will remain one word: no. When we gather all the pieces of this journey, delta V, mass ratio, orbits, radiation, atmosphere, psychology, ISRU, re-entry, and everything in between, you begin to see a truth I always try to tell my students. The universe isn't trying to make things hard for you. It simply operates according to its own rules. No celestial body in the solar system wakes up in the morning, stretches, and says, "Today I'll test humanity to see if they're smart enough." Mars doesn't hate you. Delta V isn't deliberately cruel. Cosmic rays don't target you because a committee voted on it. Heat shields don't suddenly want to burn. Rockets aren't emotional creatures. Physics never intentionally opposes you. It just stands there, in absolute neutral state and says, this is how I work. If you want to play, follow the rules. But humans, we always tend to assign emotion to places without emotion, assign motive to physical processes, and assign meaning to lifeless numbers. Because we are creatures of intuition, and intuition was forged over millions of years, living on Earth's surface, under 1G gravity, with thick atmosphere, mild temperatures, and distances the human eye can comprehend. When we step out of that cradle, all our intuition betrays us. Mars isn't complicated. We bring wrong intuitions into a place where intuition has no right to exist. We think delta V is speed. We think distance is just a bit farther. We think radiation is like X-rays. We think managing a habitat is like the ISS but longer. We think F-through is just scaled up Saboteur. All those assumptions shatter when they hit the cold plane of mathematics and physics. And it's on Mars that you see it more sharply than anywhere else. Mars is a magnifying mirror of the weakness of human intuition. It doesn't ruin your plans. It only reflects the mistakes in how you understand the universe. You underestimate mass ratio. Your ship balloons 4 times larger. You underestimate radiation. Your DNA gets pierced in silence. You underestimate psychology. Your team fractures under stress. You underestimate atmosphere. You slam into the surface faster than emergency services can respond. Mars isn't complicated. It's just honest. And honest to the point that humans feel it's cruel. But that cruelty isn't punishment. It's a lesson. Because the most beautiful thing in science isn't finding what's easy. The most beautiful thing is when you look straight at what's hard and understanding why the problem fights back is the moment I always find beautiful. Because understanding is the starting point of overcoming. When you know why mass cascade kills designs, you start looking for higher exhaust velocity engines. When you understand why landing on Mars is hard, you start thinking about retro propulsion combined with real-time AI control. When you understand why F-through isn't stable at large scale, you start designing multi-level redundant systems, or even directions that don't use chemical propellants. When you understand why radiation shreds DNA, you think about water shielding, hydrogen-rich materials, or artificial magnetic fields. When you understand why psychology erodes, you think about larger habitats, rotating artificial gravity, or robot support. Science doesn't begin from the belief that everything is easy. Science begins from the honesty that everything is hard, and Mars is the most honest opponent we have. It doesn't compromise with intuition. It only obeys the law, and only when we understand the law can we find a way to surpass it. Humans explore, not because everything is easy. Humans explore because we are curious enough to accept difficulty as part of the game. We don't go to the abyss to jump in. We go to measure how deep it is and think about whether we can build a bridge across. Mars isn't a forbidding wall. It's just a challenge, bigger than any we've ever faced. It's where mathematics speaks so loudly that intuition must fall silent. It's where our current engineering reveals all its weaknesses. It's where psychology, biology, engineering, physics collide in massive chaos. It's where every small error becomes a huge echo. It's where returning isn't a normal step, but the pinnacle of scientific honesty. Either you get it right, or you don't come back. And right at that point, I see the beauty of Mars return. Not poetic beauty, not the beauty of a flag planted on red soil, not the beauty of a speech, but the beauty of a problem big enough to force us to mature in how we understand the universe. Mars doesn't make us small. It makes us more precise. It demands we abandon intuition and replace it with clear thinking. It demands we accept that physics is more honest than we are, and honesty is the foundation of progress. One day, with engines having 10 times higher exhaust velocity than today, with lightweight yet effective radiation shielding, with AI that can run SRU flawlessly for a second, with materials that withstand 12 kilometers per s re-entry without breaking, with habitats that protect human psychology for 3 continuous years. I believe we will return from Mars, but that day is not today. Today, Mars return is a reminder that in the battle between intuition and nature, nature always wins, not because it's complicated, but because it's consistent. And we, with all our curiosity, foolishness, creativity, ambition, and mistakes, keep trying to understand it, because that's what makes us human. So let's end with what I've always believed. Nature isn't complicated. We are, and Mars is where that becomes impossible to ignore. If you want to join me on my next explorations, remember to subscribe so you don't miss any lectures. See you again where science continues to reveal the wondrous secrets of the universe.